Next, we're going to state and prove the Cauchy-Schwarz inequality, which is a very important inequality from arithmetic and mathematics and stretching all the way through functional analysis and probability. Let's denote n by 1 real valued vectors as elements of Rn. So Rn stands for the set of all n by 1 vectors with real elements. Let's take two of these in particular, v and w. So I'll write v and w are in Rn. That's element of. Their transposes are row vectors, right? If a vector is n by 1, then its transpose is 1 by n. Now, since the transpose is 1 by n and the vector is n by 1, the matrix vector product, that's a 1 by n array times an n by 1 array. It's well defined, and it's in fact a 1 by 1 array, a scalar. Namely, v transpose w is w transpose v, and it's just the summation of the element-wise multiplication of the two. If we write it the way we were writing matrix vector multiply, there's the matrix, there's the vector, and there's the matrix vector multiply. v1 times w1 plus v2 times w2 plus ... vn times wn. This is also called the inner product of the vector v with the vector w. We won't use that terminology extensively in this module, but in the upcoming linear programming module, the phrase inner product will come up more often. We could illustrate this in MATLAB, make up two random vectors of length 20, and then compute v transpose times w, or w transpose v, or the summation of the element-wise multiplication of the two. Of course, we'll get the same result for all three calculations. When a vector is inner product with itself, v transpose v, well, that's just the summation of all the elements of v squared. That's clearly a number that's greater than or equal to 0 for real vectors, and that's what we'll focus on here. This simple observation that v transpose v is always greater than or equal to 0 will be useful in the next few slides. These next few slides cover the Cauchy-Schwarz inequality. And what that inequality states is the following. Given any two real vectors, v and w, the absolute value of the inner product of v with w, in other words, the absolute value of v transpose w, is always less than or equal to v transpose v square root times w transpose w square root. Getting rid of the vector notation, it just means that if I had a collection of numbers v1 through vn and w1 through wn, then simply the summation, where the v and w's are multiplied together and added and squared, is less than the individual squares of the v's added up times the individual squares of the w's added up. That's the inequality. Over here it's written in vector form. This is the Cauchy-Schwarz inequality. Read about it in Wikipedia, for instance. So let's do the proof. Well, if either v and or w is the 0 vector, in other words, all elements equal to 0, then the inequality holds since both sides of the expression are equal to 0. V transpose w would be 0 because either all the v's or all the w's are 0. And then on the right-hand side, one of those two square-rooted terms would be 0 as well. So that clearly is true if either of the vectors are the 0 vector. So for now, let's assume that both of them are not the 0 vector. Now, recall that for any vector z, it must be that z transpose z is greater than or equal to 0. That was the thing we discussed on the previous slide at the end. That expression z transpose z is just the summation of the squares of all the entries of z. Hence, it must be greater than or equal to 0. So that certainly means that if I take the vector v and the vector w, and I scale the w vector by a scalar t and add it to v, that transpose times itself must always be greater than or equal to 0, regardless of the value of t. Right? This vector, v plus tw, is just playing the role of some z vector. So regardless of t, this is greater than or equal to 0. Another way to say that is to take that expression and minimize it over all possible values of t. Find the t which makes it the smallest. Well, what we do know is that that minimum value will always be greater than or equal to 0, because this expression is greater than or equal to 0 for all values of t. So the min must be greater than or equal to 0. If you look at this, though, it looks like it must be a quadratic function of t. Notice there's a t in both expressions and they're multiplying each other. So maybe we can use the theorem about the minimization of a quadratic function being greater than or equal to 0. Let's see where that gets us. But first we have to expand out this expression. Let's remember the distributive property for matrix vector multiplication. If we had appropriately dimensioned arrays and vectors, we can distribute matrix vector multiplication across addition of vectors, and we can also distribute matrix vector multiplication across addition of the matrices. That means that we can do some simplification on the expression v plus tw transpose times v plus tw. First, let's distribute across the second argument. So there, the array v plus tw transpose times v plus the array v plus tw transpose times tw. Next, we can distribute out the array addition. The first term becomes v transpose times v plus tw transpose times v, and the second expression becomes v transpose times tw plus tw transpose times tw. I've grouped the scalars together. There's a t squared. Next, we remember that v transpose w is the same as w transpose v. So these middle two terms can be grouped together, and I've grouped them as v transpose w. And there's two of them, and they're both scaled by t. Now go back to the fact that we know the minimum is non-negative. On the previous slide, we established this minimum is always greater than or equal to 0. But now we know an expression for the function being minimized. It's just this quadratic expression. Let's label the terms. There's a, there's b times t, and there's c times t squared. Notice that c is greater than 0. Our assumption was that w is not the 0 vector. Therefore, w transpose w is greater than 0. It's the sum of squares of at least some non-zero entries. This is precisely the setup that we worked on for the minimization of the scalar quadratic function. We know that the minimum is greater than or equal to 0 if and only if 4 times a times c is greater than b squared. That was exactly the expression. If I simply now cancel the 4, notice there's a 2 being squared. What I end up with after moving things to opposite sides is simply v transpose w, absolute value, that's what I get when I take the square root of the square, is less than or equal to the square root of v transpose v times the square root of w transpose w. And that is the Cauchy-Schwarz inequality.